Okay, so welcome to this second video on the law of the unconscious statistician. So the law of the unconscious statistician was something that we stated and used in the previous video. So the law of the unconscious statistician, often abbreviated to LOTUS for short. Conscious statistician. Okay, so the law of the unconscious statistician is that basically if you have a random variable, so let's say we have our abstract probability space over here, which is our sample space, our set of events, curly f, and our probability measure defined on this set of events, and we have a random variable x, which maps each outcome in this set here. So let's say s is an outcome in the sample space. It's going to map it onto a real number x of s, and this has to inherit the probability space structure of this, so that they are effectively isomorphic or homomorphic probability spaces. We make sure that any event in here has an event corresponding event back in here, and we make sure that the probability of any event in here is the same as the probability of the corresponding pre-image of that event back here. Okay, now the law of the unconscious statistician says that if I take another function which is g of it's going to be called g, which is going to map each value of the real numbers over here onto g of x of s. So it's going to be another function that's going to map the real numbers onto another real number. And again, we're going to let this inherit the probability space structure from here, which means it's inherited the probability space structure back from here. Then what we want to know is if we look at this random variable here, the composition of both of them, that is a random variable, and we'd quite like to know what is the expected value of y, i.e. What is the expected value of g of x well, let's just put g of x like that, because obviously usually we just write expected value of a random variable x. We don't write the expected value of x of s, or we just write, so this is our random variable g, x followed by g. The law of the unconscious statistician says that this is for discrete random variables, which is all we're going to prove it for, because it requires it requires more technical maths to prove it for the non-discrete case. For the discrete case, it is the sum of g of little x rather, over all values that x can take on, times the probability that x is equal to little x. And okay, so it gives you a way of working out the expected value of this overall random variable here, this expected value of y, which is equal to the expected value of g of x, without working out the probability distribution on here. So just by knowing the probability distribution on here, we can work out the probability distribution on here. And the way we're going to prove this is as follows. It's going to follow a very similar course to the way that we proved linearity. Okay, so when we look at the expected value of x, the expected value of some random variable x, then we know that that is the sum over every possible value of the random variable that the random variable can take on. So over all x's. So let me draw a picture again. So we have our abstract probability space here being mapped onto a set of real numbers. Now this contains only a certain number of real numbers. It contains either, because it's a discrete random variable, it contains either finitely many or countably many, but they're all over here. And basically you're going to take each one of them and you're going to ask what is the probability of that set containing that single real number x. And so we're asking what is let's say this probability space is omega prime, f prime, and p prime. Then the probability measure of this singleton containing x is what we're going to stick in here, which is the p prime of this singleton x, which is often usually instead written the probability that the random variable big X is equal to little x, or the PMF basically. But there's another way that we could think of this expected value, of working out this expected value. Remember the way that we define random variables. There will be lots of little outcomes here, loads of little outcomes here, which are all being mapped on potentially onto a single value over here. I.e., there might be a single x value here with lots of s values all being mapped onto the same one. It might not be a one-to-one map. Some of them will. I mean, we could have a one-to-one map. For instance, if I roll the dice, then I can get outcomes 1, 2, 3, 4, 5, 6, and I could map those onto the real numbers 1, 2, 3, 4, 5, and 6. So that would be a one-to-one map. And remember, you might think that's very trivial. Why have I mapped a number onto itself? Those numbers on the dice are just outcomes. They might as well just be abstract symbols denoting the outcome. The 1, 2, 3, 4, 5, and 6 in the real numbers denotes the 1, 2, 3, 4, 5, and 6 with the algebra, the field algebra, the real numbers all defined on it. So it is actually denoting a very different mathematical structure, even though you're using the same symbols. Okay, so another way of writing out this expected value of x, as we discussed in the proof of linearity, is to sum over every possible outcome in this abstract probability space. So this is omega, this is curly f, and this is p. So over every s is an element of omega, every s is an element of the sample space, times the value of x of s. So remember, s will be mapped onto its x of s, and then times the probability of that single outcome s. So the probability of the singleton set containing s. And now, because this random variable is an isomorphism, the probability, well, a homomorphism, the probability space structure is effectively the same. So p prime of the singleton containing x basically has to equal the sum of over all s. How would I write this? Over s is an element of x inverse of x. So basically, if we define x inverse of x, of this little x over here, so we take a little x in this probability space here, this standard one in the real numbers, and we take x inverse of it, and this it means, so by definition, this is going to be equal to all s, which are an element of the sample space, such that x of s is equal to little x. So I'm saying this is the set of all values or all outcomes which are going to be mapped onto x by the random variable big X. Okay, so you sum over every single outcome in the pre-image of the value x, and you add up their probabilities. That has to equal the probability that you get that single outcome x in this probability space with elements in the real numbers. So if the two probability space structures are going to have effectively the same structure, what you're basically saying is group this set together. This set is this set of outcomes is being grouped together, and we're going to now call that event just the event. We're going to demote it basically. We're going to demote it from being an event to being an outcome basically. So it's going to become really what you're doing is you're saying that whole outcome, that whole event with lots of outcomes in is being demoted to the event with just one outcome in, which is the event x. But if the probability space structure is going to be effectively the same, then the probability of this event must be equal to the probability of this event, and the probability of this event, this event here, this is an event, remember, so the probability of this event is going to be the sum of the probability of all the events containing just the singletons which make up that event. So that's what we're doing there. So basically what we can now do is we're in our expected value of x calculation, we can say that the expected value of x is the sum over all x values of x, and we can replace p prime with this sum of s is an element of x inverse of x of the probability of the singleton containing the set the set containing the singleton s. Now every s value has at least every s value in this, so every outcome in this original abstract probability space up here, so every outcome is mapped onto a single x value. So every outcome is going to be in at least one of these sets. So if I sum over all values for x possible, then at some point I'm going to come across every single s value. So we could replace this by the sum over s is an element of the whole sample space, and then all we need to do is make sure that the probability of the singleton is times by the appropriate x value, which is just what we need to do by putting x of S there times the probability of the singleton containing S. So basically, this and this are the same thing, because all we're going to do here is basically we're dividing up this set into these pre-images of the sets containing the singletons over here. So all of these, each of these sets which I've partitioned this sample space up to is being mapped onto a single outcome over here. And if I sum over every possible value of x, I'll get every single one of these, and I'll multiply each of these. This is the probability of that overall. I'll multiply it by x. So if I break it down into adding up over all elements of the sample space, and I just multiply each probability of the singleton by the x value it's going to go on to, that will be the same as this calculation here. So that's why the expected value of x is equal to that. So now basically what I can say is we're going to now try and derive the law of the unconscious statistician. So if I get another function, so let's go from here, let's put another function here which is g of well, it's going to take, it's just the function g which is going to map each of these onto another real number. Then by this formula here, the expected value of g of x is going to be equal to the sum over every possible value of the sample space of g of x of s. So that's the value of the random variable g of x, which it's the value that the random variable g of x is going to ascribe to the single outcome s times the probability of that single outcome. Now what we can do is we can say what we can do is now go backwards a step. So we can say, well, instead of summing over the entire sample space, instead I can just sum over x values and say g of x, and then I can replace this back by saying I'll sum over s as an element of x inverse of x times the probability of the singleton s. So basically what I'm doing is I'm going backwards. So here what we were doing is we were going from where were we? Where did I even write this? We were going from this to this. Now what I'm going to say is equivalently to summing over every possible element of the sample space, I could just sum over every possible value of x. I know what g of x is going to be for those values of x, and then I can just say over each of these values of x, you need to sum over all the outcomes which were in the pre-image for that value of x. So basically what I'm doing is, if we go back to this picture, instead of summing over every single value of s, I'm grouping it up and saying let's sum over each of these instead. So over each of these has a fixed x value, and therefore it has a fixed g value because they are all mapped onto the same x, so they're then also all going to be mapped onto the same g. So all of the elements in one of these sets are going to be mapped onto the same x, and therefore they're going to be mapped onto the same g. So I can group it back up into these and say the g value that they're all going to be mapped onto is g of x. And then I can say, okay, what's the probability of this event? Well, it's going to be the sum over every s value that's in that event of the probabilities of the singletons, and I can now replace that with the probability, well, p prime of the singleton x, which is equal to, often more commonly denoted, the probability that the random variable x is equal to little x. So that is why it becomes the expected value of g of x, this compound random variable, g of big X, I should write there, is equal to the sum over all possible values that the random variable big X can take on of g of that value of little x times the probability that big X is equal to little x. Okay, so that is the derivation of the law of the unconscious statistician for discrete random variables.